Hello everyone, greetings from ACE Engineering Academy. Myself, Professor Rajendra Garashe. I have done MTech from Indian Institute of Science, Bangalore. I was the All India 7th ranker in the GATE examination and currently working as a faculty member at ACE Engineering Academy, Hyderabad. I am having a teaching experience of more than 10 years. So, in today's session, we are going to discuss the important concepts in power electronics for GATE 2023. So, we are having the number of important concepts. In that, particularly, we are going to discuss the voltage control in inverters. So, my dear friends, why the voltage control is required in the inverter? Because if you check, inverter is the circuitry that converts fixed DC to variable AC. Inverter gives the output in the form of variable voltage, variable frequency. Alright. So, if my inverter output voltage changes, okay, then definitely whatever the other loads, those are connected to the inverter circuitry, the functioning of those loads will be getting affected. Alright. And if you check, in the inverters, single phase inverters and 3-phase inverters, you might be familiar with those circuits. Voltage source inverters where the input is a fixed DC and your output varies according to the input na, and generally to the inverter circuitry the input is provided with the help of the chopper circuitry. So if the input voltage to the inverter changes, definitely its output voltage will be getting affected. Okay. So we require, yes, to control the voltage in inverters. So there are various ways to control the inverter output. Okay. So various ways means we can add the external block either at the input side of the inverter or at the output side of the inverter. We can connect the two inverters in series, or the very important technique, that is the internal control of the inverter, means the control is within the inverter itself. It is known as the pulse width modulation technique. In the pulse width modulation, again there are three types: single pulse width modulation, multiple pulse width modulation and sinusoidal pulse width modulation technique. These three techniques are very important. If you check the previous GATE question papers, GATE as well as ESE, you can refer. The most of the questions they have asked based on the PWM technique only. So in today's session, we are going to discuss more about the single pulse width modulation technique. Okay, in detail, the operation of a single pulse width modulation technique, and at the end we will be discussing about the previous year questions. Okay, yeah. So voltage control in inverter is required for survive with the variation in the input DC voltage. Yes, just now whatever we discussed. Allow adjustable voltage to the load. Alright. Next, now certain loads like a induction machine. If you check the induction motor drive, that is the speed control of induction motor. In the speed control of induction motor, we are having the very famous method, that is nothing but the V by F ratio control. Alright. So we are having the circuitry, that is the inverter, that gives the output in the form of variable voltage and variable frequency. Okay. So therefore, if I go on changing the voltage and frequency in proportion, I can maintain the V by F ratio constant. Okay. So here certain loads such as the variable frequency induction motor drive need simultaneous control of frequency and voltage. The frequency of inverter output can be controlled by varying the conduction period of the switches. Alright. Voltage control may be achieved by any of the following techniques. Yes, as I said, the techniques are external control of DC input voltage of inverter. External control of DC input voltage means, external control means we are adding the external block at the input side of the inverter. So here the control is not within the inverter. We are adding the external block at the input side of the inverter. Alright. Second, external control of AC output voltage of inverter. In this technique, we are adding the external circuitry or the external block at the output side of the inverter, at the output side of the inverter. In this also, the control is not within the inverter, okay? And third is internal control of inverter. Yes, third one is very, very important. Internal control of inverter means the control is within the inverter itself, okay? So first two are the external controls and third one is the internal control of inverter. Let us have a look about external control first. So external control of DC input voltage of inverter, right? So DC input voltage of inverter. So here we are having the inverter, all right? Next to the inverter we have connected the load. As this technique is external voltage control using DC to DC converter. Now DC to DC converter is definitely connected at the input side of the inverter, all right? Here input to the DC to DC converter is a fixed DC. With the help of DC to DC converter, that is nothing but the chopper, we can convert this fixed DC to the variable DC. And that variable DC is given as an input to the inverter, given as an input to the inverter. Now you can check, yes, if I change the input voltage to the inverter, definitely my output voltage will change, na? So accordingly we can control the output voltage of the inverter. But here important to note that we are controlling the output of DC to DC converter actually. Due to that, the input to the inverter circuitry changes, and based on that input is changing, so therefore output of the inverter circuitry will change. Okay, so that's why it is the external control at the input side of the inverter, at the input side of the inverter. So this is the one way. Next, input voltage control of inverter using AC voltage controller and uncontrolled rectifier. So one way we discussed is with the help of DC to DC converter. Second possible way we are having is, yes, this is your inverter circuitry. At this side we are having the load, and to the inverter, yes, we are giving the output of uncontrolled rectifier. Uncontrolled rectifier is connected to the output of AC voltage controller. So here you will be having the input is a fixed AC. Your AC voltage controller will convert that fixed AC to variable AC. Uncontrolled rectifier will convert that variable AC to variable DC, and that variable DC is given as an input to the inverter circuitry. So here again I am changing the input to the input DC voltage to the inverter. So definitely the output voltage of the inverter will change. Yes or no? Right? Next, input voltage control of inverter using controlled rectifier. Yes, this is the one way. So here controlled rectifier we are using. Input to the controlled rectifier is a fixed AC. Controlled rectifier is nothing but your thyristor based rectifiers. Those converts fixed AC to variable DC. That variable DC is given as an input to the inverter circuitry, right? So if I am giving the DC variable input to the inverter, definitely my output will be getting controlled. Output of the inverter will be getting controlled. Okay. So these are various ways by which we can control the output of inverter by externally controlling the input of the inverter. So you can check, we have added the external blocks at the input side of the inverter now, right? Whether here in this case, whether the control is within the inverter? No, control is not within the inverter. All right. Next, input voltage control of inverter using uncontrolled rectifier and DC to DC converter. Yes, this is again one of the possible way, right? So we are having the number of possible circuits. You can go through it. And one more thing, they have not asked a single question based on the external control. You can find the number of questions based on the internal control only. All right. So next, external control of AC output voltage of inverter. External control of AC output voltage of inverter means now at the output side of the inverter we are going to add the blocks. Add the blocks in nothing but the different converters. Okay. So here, yes, we can connect the AC voltage controller. We can use the series connection of the inverters. Let us discuss in short. External control of AC output voltage of inverter using AC voltage controller. So here you are having the inverter. Input to the inverter is a fixed DC, right? So my inverter convert that fixed DC to the AC, variable AC, all right? And that variable AC is given to the AC voltage controller. Input to the AC voltage control is the output of your inverter, and my AC voltage controller again will convert that AC to the variable AC and so on. Okay, so we can control the output to the that is voltage across the load accordingly, right? And one more is series connection of two inverters. We can connect the two inverters in series, and yes, this is about the series connection of inverters. So we are going to connect the two inverters in a series. So the block diagram is like this. You can check. This is the first inverter. Here it is the second inverter. Output of the first inverter is connected to the primary winding of the one transformer. Output of the second inverter is connected to the primary winding of the second transformer. The secondary windings of both the transformers are connected in series. Both the transformers are connected in series. Input to both the inverters is from the same supply. Okay. So outputs of the two inverters are connected in series here. And across the series combination, we have connected the load. So here V0 is equal to V01 plus V02. One more thing. Here, let us consider inverter 1 and inverter 2. These are a single phase full bridge inverters. We know in the single phase full bridge inverter circuit, we are having the four switches now, S1, S2, S3 and S4. Recall the circuit diagram of single phase full bridge inverter. We are having the four switches now. Alright. So these consist of the four switches. This inverter consists of the four switches. Now we are going to operate the switches of both the inverters in such a way that we will be getting some phase displacement between the output voltages of both the inverters. So here I have shown output voltage of first inverter, that is a V01. This is the output voltage of the second inverter, that is a V02. So what we are doing here, during this is your time or you can write omega t, doesn't matter. Okay, as these are the angles I have shown, so let me write here it as omega t, right, omega t. So now tell me, yes, for the first inverter from this point till this point, what is the output voltage? Output voltage is V, is nothing but same as that of the supply voltage. So can we say that during omega t 0 to pi, from the first inverter, switches S1 and S2 will be in a conduction mode. Alright. Next, from pi to 2 pi, we are going to turn off the switches S1, S2 and we are going to trigger the switches S3, S4. So I will be getting the output voltage minus V. Similarly, again S1, S2 on, again S3, S4 on, S1, S2 on, and again so on. So this is my 180 degree square wave output of a first inverter. Now we are going to operate the second inverter. V02 is nothing but the output of your second inverter. Alright. So if this is a 1:1 means this is a V01 voltage, this is your V02 voltage. Yes or no? If this is V01, definitely this is V01. If this is V02, definitely this is V02. Here, yes, here we are going to operate the switches in a second inverter in such a way that, yes, from this point, this angle is like a phi, from omega t phi till omega t pi plus phi. You can check, this is phi, this is pi plus phi. During omega t phi to pi plus phi, I am going to trigger the switches S1, S2 of inverter 2. So if I trigger switches S1, S2 of inverter 2, what will be my output voltage? Output voltage is equal to Vs, which is equal to V in this case. So here what is happening? Yes, I have turned on the S1, S2 of inverter 1 from 0 to pi, but whereas we are going to trigger the switches S1, S2 of second inverter after some delay of phi angle. This is your delay of phi angle, right? So phi to pi plus phi, S1, S2 will be in a conduction mode. Pi plus phi till 2 pi plus phi, S3, S4 switches of inverter 2 will be in a conduction mode. So if S3, S4 conducts, tell me what is the output voltage of second inverter? Definitely it is the minus V, na? Right? And similarly, positive and negative cycle. Positive cycle and alternately will be getting the negative cycle. Now if you check the first inverter and the second inverter output. Both are the square waves, na, 180 degree square wave mode. But the thing is, yes, both are not in phase. You can check V02 is lagging to V01 by how much angle? By angle phi radian, na? Yes or no? By angle phi radian. So therefore, this is the output voltage of my second inverter. This is the output voltage of the first inverter. Alright. Now, what will the load voltage waveform? Come on. Load voltage waveform is nothing but V01 plus V02, na? Right? So if you check the waveform, during omega t 0 till omega t equal to phi, V02 is a minus V. This is a plus V. So what is V01 plus V02? Yes, V plus minus V. That is equal to 0, na? So I will be getting the V0 is a 0 here. I will be getting V0 is equal to 0. Doing 0 to phi. During phi till omega t equal to pi. This is phi. This is a pi. From omega t phi till omega t equal to pi. What is the load voltage? V01 is a V. V02 is also V, na? So it is V plus V means 2V. We will be getting the V0 is equal to 2V. Alright. This will continue till which instant? Till pi. After pi, what will happen? From pi till pi plus phi. From omega t equal to pi till omega t equal to pi plus phi. This is minus V. V02 is a plus V. So what is the addition? 0, na? So we will be getting again 0 here. Similarly, you can check from pi plus phi till this 2 pi. This is minus V, this is also minus V. So we will be getting the output is minus 2V. And similarly from 2 pi to 2 pi plus phi, it will be 0 and again positive pulse 0, negative pulse 0 and so on. So we are getting the output is a quasi square wave, na? Right? V01, V02, these two are the square waves. But load voltage is your quasi square wave. Now tell me, if I change this angle phi, if I change the angle phi, because what should be the value of angle phi? We can select any value of angle phi. That we are controlling, na? Unless and until I trigger S1, S2, my output voltage of the second inverter will not be positive, na? Yes or no? Right? I can trigger S1, S2 either at this point. I can trigger S1, S2 either at this point or at this point. It is up to me. Alright? So therefore, I can select any value of phi. Now if my phi is changing, whether the width of this pulse will change? Definitely, width of the pulse will change. And accordingly, I can change the output voltage. That is nothing but the voltage across the load. Alright? So this is the one of the method by which we can control the load voltage. Right? How we are controlling? We are connecting the two inverters in series. Right? Two inverters in series. Now, suppose if we want to draw the phasor diagram, yes, how we have written this formula, let us discuss. Suppose if we want to draw the phasor diagram of V01 and V02, yes, let me first draw the phasor diagram of V01. Phasor diagram of V01, yes, this is a phasor of V01. Let me consider this is a V01 phasor. Next, if this is a V01 phasor, where will be the phasor of V02? Come on. V02 is lagging to V01 by how much angle? Phi, na? So therefore the phasor of V02 will be like this. This is your V02. And what is the angle? Angle is phi. Angle is a phi. Right? V01, V02 both are the square waves. But these two are not in phase, na? So they are having some phase displacement. Now from this, if we want to draw the phasor of V0, V0 means V01 plus V02, na? So we can draw, yes, V0 phasor. It will be like this. This is the V0 phasor. Right? So how to write the V0 expression? By using the law of parallelogram, na? It is equal to under root V01 square plus V02 square plus 2 times V01 into V02 and into cos of angle between these two. Alright. So you can check, this is my V0, that is output voltage. It depends on the angle phi. Alright. Angle phi is the phase displacement angle between V01 and V02. All right. So this is the one of the method by which we can control the load voltage. Okay, but here we require the two inverters. Okay, we require the two inverters. All right. Next. Now till now whatever we discussed so far in the previous gate examinations or ESC, they have not asked the questions. Okay, right. But this is only for your understanding. Okay. Next, they may ask the question. Now we are going to discuss the internal control of inverters. Very, very important point. Okay, internal control of inverter. So internal control means now the control is within the inverter. Control is within the inverter. So in the internal control of inverter, yes, control is within the inverter, and there are different ways in order to control the output voltage of inverter. Yes, those are single PWM, multiple PWM, and the sinusoidal PWM. It is known as the pulse width modulation technique. Yes, in this technique the voltage control of inverter is obtained by varying the pulse width of the output modulated wave. This scheme is most popular. Yes, this scheme is most popular, efficient and economical, because this is not only provides the controlled output voltage but also eliminates the lower order harmonics. We will discuss how this technique is used for elimination of the harmonics also. Okay. Next, the selection of a suitable PWM technique depends on the range of voltage control and performance. Yes. So pulse width modulation, PWM technique. In an internal control, we are having the PWM technique. Okay, pulse width modulation. So pulse width modulation means what? We are going to modulate the width of the pulse, okay, right. So that's why it is a pulse width modulation, right. PWM is widely used in industrial inverters to control the output voltage and to reduce or eliminate the lower order harmonics. It is the most efficient. Yes, same thing we discussed. The commonly used PWM techniques are single PWM. In a single pulse width modulation technique, corresponding to each half cycle of output voltage, we are going to get only one pulse. So that's why it is a single PWM technique. Next one is the multiple PWM technique. In a multiple PWM technique, corresponding to each half cycle of output voltage, we are going to get multiple number of pulses. Okay, but the width of each pulse is same or equal. And third one is the sinusoidal PWM technique. Here also, corresponding to the each half cycle of output, we are going to get multiple pulses in the output, but the width of each pulse is not equal. Okay, so here also we are getting the multiple pulses corresponding to each half cycle. Here also we are going to get the multiple pulses corresponding to each half cycle, but the difference is here the width of each pulse is same. Here the width of each pulse is different. Are you getting the point? Okay. And next one is the single PWM. In a single PWM, we are having only one pulse, right, corresponding to each half cycle. Next, so let us discuss now single PWM technique, single pulse width modulation technique. Very, very important. Okay. Yes. And it is interesting even. Yes. In this PWM technique, there is only one pulse per half cycle. Yes. Just now whatever we discussed. And the width of the pulse is varied to control the inverter output voltage. The gating signals are generated by comparing a rectangular reference signal of amplitude AR with a triangular carrier signal of amplitude AC. So here we are having the two signals. One is reference signal. Reference signal is a rectangular. And second one is the carrier signal. Carrier signal is your triangular signal. Carrier signal is a triangular signal. Always keep in mind, in all the PWM techniques, the frequency of the reference signal is always equals to the frequency of output of your inverter, which is equal to frequency of fundamental component of your inverter. Okay, right. The frequency of the reference signal determines the fundamental frequency of the output voltage. All right. Yes. Generation of gating signals and output voltage of single phase full bridge inverters are shown. Okay, yes, let us discuss. So this is the block diagram which is applicable for all the PWM techniques. single PWM, multiple PWM as well as sinusoidal PWM techniques. Let us discuss. It is very simple. It is having major two blocks only. One is the comparator block and second one is the trigger pulse generator block. Okay. Here input to the comparator are two signals. One is a carrier signal. VC is nothing but the carrier signal and VR is nothing but the reference signal. Okay. In a single PWM technique, carrier signal is having a nature like a triangular and reference signal is your rectangular signal, right? Rectangular signal. Here comparator input to the comparator is VC and VR. The comparator compares the values of VC and VR. Based on that, the comparator gives the output either in the form of 0 or 1, that is low or high. And based on the output of your comparator, the trigger pulse generator will either generate the triggering pulses or it will not generate the triggering pulses. So whether this block has to generate triggering pulses or not, who decides? Output of the comparator decides. And trigger pulse generator output is given as an input to your single phase inverter, right? Here it can be single phase, here it can be your single phase half bridge, single phase full bridge, any inverter. Okay, means if you check, if I consider here single phase full bridge inverter, recall the circuit diagram of single phase full bridge inverter. Single phase full bridge inverter consists of 4 switches na, S1, S2, S3 and S4. Okay, so out of these 4 switches, to which switch we need to provide the triggering pulses, that will be decided by this trigger pulse generator block. Okay, trigger pulse generator. So simple block diagram we are having, right? So I am repeating it, please listen it carefully. This is a comparator which compares the two inputs VC and VR, right? Based on the output, based on this the comparator give the output either in form the 0 or a 1, right? And trigger pulse generator will either generate the triggering pulses or it will not generate the triggering pulses. And based on that, the respective switches in an inverter, either those will be triggered or triggering pulses will not be provided to those switches, right? Simple block diagram. Now let us discuss in a single PWM. Yes, here we are having the reference signal, that is a rectangular wave. Okay, this is a reference signal. AR is nothing but the amplitude of reference signal. AR is the amplitude, that is the peak value of reference signal. So this is your reference signal. I have shown na, this is a rectangular which is equal to reference signal. Second, we are having a carrier signal. Carrier signal is a triangular. The blue one is a carrier signal. It is a triangular. It is a triangular. These two signals we have given as an input to the comparator na, as an input to the comparator. Now we need to here use the logic. You need to develop the logic in comparator in such a way that if VC becomes greater than VR, this is carrier signal na, that is nothing but VC. This is a reference signal which is nothing but VR, which is nothing but VR. Okay, so amplitude of carrier signal you can check, it is a AC. AC is the amplitude of carrier signal. Now if VC is greater than VR, the output of your comparator will be 1. So let me write, if VC is greater than VR, then output of comparator is equal to high and trigger pulse generator will generate the triggering pulses, and those triggering pulses are provided to switches S1 and S2. VG1, VG2 are nothing but the triggering pulses, right? Those are provided to the switches S1, S2. Where the switches S1, S2 are present? Switches are present in single phase full bridge inverter. Alright, so here when VC is greater than VR, output of my comparator is 1, trigger pulse generator will generate the triggering pulses. So during this interval, we are going to provide the triggering pulses to switches S1, S2, Now we can check before this point, yes, before this point, VC is less than VR na? If Vc is less than Vr, Vc means this blue one, Vr means this rectangular yellow one. Vc is less than Vr means output of comparator is 0. Trigger pulse generator will not generate the triggering pulses. So if the trigger pulse generator is not generating the triggering pulses, so I am not providing the triggering pulses to any of the switch. I am not providing the triggering pulses to any of the switch. So tell me, if all the 4 switches are in an off state during this interval, what is the output voltage of my inverter? Obviously 0, na? So output voltage of the inverter we are getting, it is a 0. Is this clear? I am saying that during this interval, Vc is less than Vr, output of comparator is 0, your trigger pulse generator will not generate the triggering pulses. So all the 4 switches will be in an off state. So output of your inverter will be 0. We are getting the 0 output voltage. Alright. Next, from this point till this point, Vc is greater than Vr. If Vc is greater than Vr, what is the output? What is the output of comparator? Comparator output is high. Trigger pulse generator will generate the triggering pulses, and we are providing those triggering pulses to switches S1, S2. Now tell me, in a single phase full bridge inverter, when S1, S2 are in a on state, what is the output voltage? Output voltage is equal to Vs, na? So therefore during this interval, we are getting V0 is equal to Vs, right? You can check the waveform. V0 is equal to Vs. V0 is equal to Vs. Alright, this is a Vs. Next, after this point till pi, from this point till pi, what is happening? Vc is less than Vr. Output of comparator is 0, right? Trigger pulses are not generated. All the 4 switches will be in an off state, right? So here we are not providing the triggering pulses. So therefore, what is the output voltage of your inverter? Output voltage of your inverter will be 0. This will till pi. Yes or no? Next, after pi, what is happening? Again, these two, right, are Vc and Vr. These are the inputs to the comparator. If during pi to 2 pi, if you check from this point, yes, from omega t equal to pi till this instant, from omega t equal to pi till this instant, yes, Vc is less than Vr. If Vc is less than Vr, output of comparator is 0. Output of comparator is 0, so therefore triggering pulses are not generated. You can check from this point till this point, triggering pulses are not provided to any of the switch, not to S1, 2 or your S3, S4 also, right? Not triggering pulses are provided. So what is my output voltage? 0. Similarly, you can check from this instant till this instant, Vc is greater than Vr. So output of comparator is 1. Trigger pulse generator will generate the triggering pulses, and those triggering pulses are now provided to the switches S3, S4. So here you can check, we are providing the triggering pulses to switches S3, S4, to switches S3, S4. Vg3, Vg4 means triggering pulses to switches S3, S4. So tell me, in a single phase full bridge inverter, when S3, S4 are in a on state, what is the output voltage? Output voltage is a minus Vs, na? So we are getting here negative pulse in output. Similarly, you can check from this point till this instant, Vc is less than Vr. Trigger pulse generator will not generate the triggering pulses. So what is my output voltage? Output voltage is 0, right? So this is a simple single pulse width modulation technique. As I said, in a single pulse width modulation technique, corresponding to each half cycle of output, each half cycle, 0 to pi, your output is having positive half cycle. Pi to 2 pi, output is having negative half cycle. So corresponding to each half cycle, in the output we are having how many pulses? Only one pulse, na? Right? So therefore it is known as the single pulse width modulation technique, single PWM technique. Alright? Next, now we are going to derive the expression for RMS value of this output voltage, RMS value of the V0. Okay? So for this, let us consider the width of this pulse. This is a pulse, na? Yes or no? Right? What is the width of pulse? Width of pulse, I am considering it as a 2D. Okay? So let me write pulse width pulse width is equal to 2D. Pulse width is equal to 2D. Alright. Now let us derive the expression of V0 RMS. RMS value of output voltage. RMS value of output voltage. RMS output voltage. V0 RMS. V0 RMS. Yes. If you observe the V0 waveform carefully, whatever the waveform we are having from 0 to pi, the same kind of waveform we are having from pi to 2 pi, but the only thing is it is a negative. So you can find the RMS value either over 0 to pi or 0 to 2 pi. You will be getting the same answer. Okay, you will be getting the same answer because the square of positive is positive, square of negative is again it is a positive. Okay, you can easily understand. So here I am finding the V0 RMS over only pi, 0 to pi. So it is 1 by pi integration over 0 to pi. But between 0 to pi, you can check from this point, this is 0 na? From this point till this instant output is 0. From this instant till this instant output is a non-zero, and from here till pi output is again 0 na? So effective interval between 0 to pi, the effective interval is only from this instant till this instant. Let us find what is this instant. Yes, this is 0, this is pi. So exactly center point is a pi by 2 na? Yes or no? This is your pi by 2. Now tell me, this pulse width we considered a 2D na? 2D. Out of this 2D, 50% of the pulse width is before pi by 2. Yes or no? This total angle is a pi by 2. In that 50% of this pulse width, total pulse width is 2D. So 50% of that 2D is only D na? So can we say that yes, this instant is like a pi by 2 minus this 50% of the pulse width. What is the 50% of pulse width? It is a D. So I can write it as pi by 2 minus D. Is this clear? This total is pi by 2. This is 2D. 50% of the 2D is D. So pi by 2 minus D means this instant. Similarly, can we write this point is pi by 2 plus D? Pi by 2 plus D. Is this clear? Pi by 2 minus D, pi by 2 plus D. Now let us find the RMS. Integration from pi by 2 minus D till pi by 2 plus D. Pi by 2 minus D till pi by 2 plus D. Right? Yes, what is the value? Vs. So it is a Vs square into d omega t to the power 1 by 2 na? To the power 1 by 2. Let us simplify. It is equal to Vs upon root pi. I am taking Vs square outside, this pi also outside. Integration of 1 d omega t, it is omega t na? Omega t. Limit pi by 2 minus d till pi by 2 plus d to the power 1 by 2. So it is equal to Vs upon root pi, yes, into, put the limit pi by 2 plus d minus in bracket pi by 2 minus d. So it is like a 2d na? To the power 1 by 2. So what is V0 RMS? Under root 2d, V0 RMS is equal to under root 2d by pi into Vs. Under root 2d by pi into Vs. That is supply voltage. Now you can check V0 RMS, that is output voltage of inverter, is proportional to square root of pulse width na? So if I vary this pulse width, I can control the output voltage of inverter. Are you getting the point? Okay. How to vary the pulse width? So for varying the pulse width, either you can vary the amplitude of the reference signal, alright, or you can change the amplitude of the carrier signal. If you increase the amplitude of the carrier signal, the slope of this carrier signal waveform will be getting changed, and accordingly your pulse width will vary. Are you getting the point? Okay. So you can find V0 RMS either with this technique, or this is like your Cauchy square wave na? We know how to find the RMS value. In both the ways you will be getting the same answer. Okay, right. Next, now this is about the RMS value. It is fine. They have asked some questions related to this expression even. Okay. Next, Fourier series analysis of the output voltage. Very, very, very important. Right. Now we are going to discuss how to find the Fourier series expression of this output voltage waveform. Right. Now tell me, V0 waveform. This is a Cauchy square. Is it a even or odd function? Definitely it is a odd function, na? Yes or no? So V0 is a odd function. V0 output voltage is odd function. And recall from Fourier series properties. If we are having the odd function, what is the value of an? An is 0. What is the value of a0 by 2? a0 by 2 means the average value of the function over one period. Average value of function is equal to 0. Yes or no? Average value is a 0, na? Whatever the positive width we are having, the same negative width we are having. So it is the average is 0. So only thing is we need to find Bn. We need to find the Bn. How to find the Bn? We know if the function is odd, then Bn is equal to 4 by 2 pi integration from, yes, 0 to pi, na? But in between 0 to pi, the effective interval is pi by 2 minus d till pi by 2 plus d. Okay? Pi by 2 minus d till pi by 2 plus d. During this interval, what is the V0 value? It is a Vs, na? Vs into sine of n omega t d omega t. Let us simplify it. It is equal to, yes, take this Vs outside. It is the 4 Vs by 2 pi means 2 Vs by pi. 2 into Vs by pi into integration of sine of n omega t minus cos of n omega t divided by n. Limit pi by 2 minus d till pi by 2 plus d. Let us take this divided by n outside. So it will become 2 Vs upon n pi into bracket, yes, cos of, I am writing it as n pi by 2 minus nd plus cos of n pi by 2 plus nd. Sorry, minus. So here it is a plus and this should be the minus. Yes, no? Already minus is present. So for upper limit that will be like a minus. For lower limit it will come as a plus. So it is like a cos of a minus b minus cos of a plus b. Yes or no? What is the cos of a minus b minus cos of a plus b? It is like 2 times sin a into sin b, na? So I can write Bn is equal to, therefore Bn is equal to 2 Vs upon n pi. 2 Vs upon n pi into 2 times sin of n pi by 2 into sin of nd into sin of nd. Yes, no, right? Sin of nd. So therefore Bn is equal to 4 Vs upon n pi into sin of n pi by t, n pi by 2, sin of n pi by 2 into sin of nd, sin of nd. So now here d is nothing but pulse width is 2d, na? So d is nothing but 50% of your pulse width. Okay. Here now tell me, here it is sin of n pi by 2. If n is even, n is even means 2, 4, 6, 8, 10, etc. You can check if n is 2, it will become sin pi, na? Sin pi is 0. If n is equal to 4, sin of 4 pi by 2, sin of 4 pi by 2 means sin 2 pi, it is 0. Similarly, you can check n is equal to 6, n is equal to 8, etc. So can we write for all even values of n, this term will become 0, means Bn is 0. Therefore, for even values of n, for even values of n, Bn is equal to 0. Bn is equal to 0 because sine of n pi by 2 is 0. Next, so only odd values of n we are having this expression. For odd values of n, for odd values of n, what is Bn? Bn is equal to 4Vs upon n pi into sine of n pi by 2 into sine of nd, into sine of nd. Okay, so this is only for odd values of n. Even values of n are Bn is 0. Okay, so therefore we can write Fourier series expression of V0 is equal to summation over n is equal to 1, 3, 5, 7 up to the infinity. Yes, 4Vs by n pi, 4Vs upon n pi into sine of n pi by 2 into sine of nd into sine of n omega t. The meaning is, in the output voltage of single phase, in the output voltage of single PWM technique, all even harmonics are absent, only odd harmonics are present, only odd harmonics are present. Okay, next, so now I am going to represent this V0 is equal to, please listen, V0 is equal to, put n equal to 1, it will become 4Vs by pi into sine of pi by 2 na, sine pi by 2 means it is a 1, so 4Vs by pi into 1 into sine d into sine of n omega t. This is for n equal to 1. This is algebraic sum na, so I have written plus. Put n equal to 3, you will be getting 4Vs upon 3 pi into sine of 3 pi by 2 into sine of 3d into sine of, I am writing this side, into sine of 3 omega t plus n is equal to 5, so it will become 4Vs upon 5 pi, simply put here n is equal to 5, 4Vs upon 5 pi into, yes, into sine of 5d into sine of 5 pi by 2 into sine of 5 omega t na, and plus so on, and plus so on. So now, yes, this is your output voltage at n equal to 1 na. So can I say that this is nothing but your fundamental frequency output voltage, right? In the output voltage of inverter, fundamental, third, fifth, seventh, ninth, etc. all are present. N is equal to 1 means fundamental component. After that, whatever we are having 3, 5, 7, 9, 11, 13, etc. all these are the harmonics, that is the unwanted contents we are having. Okay, next. So this is your output voltage at a fundamental frequency, that is V01. This is output voltage at n equal to 3 na, at n equal to 3 means this is V03, output voltage at third harmonic frequency. Similarly, this is output voltage at fifth harmonic frequency, means this is V05, V05, and similarly we are having 7, 9, etc. Alright, so sometimes they ask the question, in a single pulse width modulation technique, the pulse width is so and so, what is the RMS value of fundamental component of output voltage? So RMS value of fundamental component output voltage means this is your output voltage at fundamental frequency na, you need to find the RMS, okay, of this, we will discuss. Yes, so let me write output voltage at fundamental frequency. Now output voltage at a fundamental frequency, yes, V01 is equal to 4Vs by pi into sine of d into sine of n omega. Sine of n is 1 na, so it is sine of omega t. N is 1 means it is only omega t. All right, so that will be 4Vs by pi into sine of d into sine of omega t. Yes, no, sine of omega t. Now tell me, this is your fundamental component output voltage. It is a sinusoidal function na. So what is the peak value of that sine wave? Peak value of the sinusoidal function is this one. Yes, no. So this indicates the V01 peak value of fundamental component output voltage. V01 peak is equal to 4Vs upon pi into sine of d. Now from this tell me, what is the V01 RMS? V01 RMS, we know for any sinusoidal waveform, yes, V01 RMS, we know for any sinusoidal waveform, RMS value is peak divided by root 2 na. So simply divide this term with a root 2. So I will be getting 2 root 2 into Vs upon pi into sine of d, right? 2 root 2, right? 4Vs by pi sine d divided by root 2 na. So it is like a 2 root 2 by pi into Vs into sine of d. Is this clear? This is a V01 RMS. Similarly, we can write V03 RMS. Similarly, I can write V03 RMS. V03 RMS. Tell me the peak value of the third harmonic component. 4Vs by 3 pi into sine 3 pi by 2. Sine 3 pi by 2 means sine 270. That is minus 1 na? Right. Into sine of 3d. So it is 4Vs by 3 pi. 4Vs by 3 pi into sine of 3 pi by 2 means minus 1. Into minus 1 into sine of 3d. Sine of 3d. Yes or no? So the divided by root 2. Divided by root 2. So we can write it as minus of that 2 root 2 upon 3 pi. It is a negative we are getting into sine of 3d. Right? This is V03 RMS. If they ask only magnitude, you are required to write only this magnitude, no negative sign. If they ask only magnitude, okay? This is your V03 RMS. V03 RMS. All right? Next, similarly, we can write V05 RMS and so on, right? Not required. Now, we are going to discuss one important point. How this technique is used to remove the harmonics, okay? To remove the harmonics. Very, very important point. Yes. Let us discuss. For elimination of third harmonic, from output voltage, of inverter, required pulse width. Let us discuss. If we want to remove the third harmonic from the output voltage, okay? So third harmonic from the output voltage means V03 should be equal to 0. You can check the Fourier series expression. This is the Fourier series expression of my output voltage, na? Inverter output voltage. If I want to remove the third harmonic, means corresponding to the third harmonic, the output voltage should be 0. So V03 should be 0, na? V03 should be 0. Now what is the V03? 4 Vs by 3 pi sine of 3 pi by 2 into sine of 3d into sine of 3 omega t is 0. Yes or no? So we need to write 4 Vs upon 3 pi into sine of 3 pi by 2 into sine of 3d into sine of 3 omega t. This should be equal to 0. This should be equal to 0. Are you getting the point? This is your V03 I have written. Now tell me, if I want this right hand side to be equal to 0, if this right hand side is to be 0, required to be 0, then please listen, then whether this 4 Vs by 3 pi, it can be 0? No. 4 Vs by 3 pi means what? Vs is the constant input voltage to the inverter. It is a non-zero, na? 4 is constant, 3 pi is also constant. So this term cannot be 0. Next, sine of 3 pi by 2, we know sine 3 pi by 2 is a minus 1, na? So this term also is not 0, is non-zero. Now, what this sine of 3 omega t indicates? Sine of 3 omega t, it indicates only the function. Yes or no? This indicates your V03 is a sinusoidal with a frequency of 3 into omega. Right? So this is general term, that is a function, it indicates the instantaneous values. So if I want the right hand side to be equal to 0, the requirement is this sine of 3d should be equal to 0. Then and only then you will equate this term to be is equal to 0. Okay. So therefore we can write sine of 3d should be equal to 0. Now tell me, sine of 3d is 0 means 3d is equal to sine inverse of 0, na? 3d is equal to sine inverse of 0. So tell me, what is the sine inverse of 0? Therefore 3d is equal to sine inverse of 0. If you put in your calculator, it will show 0. Sine of pi is also 0, na? Sine 2 pi 0, sine 3 pi 0, sine 4 pi 0, and so on. Right? So sine inverse of 0 can be 0, pi, 2 pi, 3 pi, 4 pi, etc. Alright. Now from all these values, we need to select valid values. We need to select the valid values. So let us check for 3d equal to 0. For 3d equal to 0, I am selecting 0 first. 3d equal to 0. So tell me, if 3d is equal to 0, what is the d? D is equal to 0 by 3, na? That is equal to 0. If d is 0, what is the pulse width? Pulse width is 2d. It is a 0. So tell me, pulse width is 0 means whatever the output voltage you are having. Yes, here pulse width 0 means this 2d value is 0. So if the pulse width is 0, your overall output voltage of inverter is 0. Not only the third harmonic. If pulse width is 0, your V0 will be 0 for all time. Is it acceptable? No, it is not acceptable. Are you getting the point? I am saying that 2D 0 means this pulse width is 0. Pulse width 0 means your output voltage of inverter is a 0. So in that output voltage, not only third harmonic, but overall output voltage is 0, means no harmonics are present, no fundamental component is present. Right? So 2D is equal to 0 is not acceptable. Right? Yes. This is not acceptable. Next, let us check for 3D equal to, second is pi, na? 3D equal to pi. So 3D equal to pi. So if 3D is equal to pi, what is the D? D is equal to pi by 3. So what is 2D? 2D is equal to 2 pi by 3, na? It is a 2 pi by 3 radian. 2 pi by 3 radian. So 2 pi by 3 radian means 120 degree. Let us check whether it is acceptable pulse width or not. Here, if you check the waveform of V0, single PWM V0 waveform. As we know, in a single pulse width modulation technique, corresponding to each half cycle of the output, right? How many pulses we are having? We are getting only one pulse, na? So for each half cycle, we want only one pulse in output. So tell me, what can be the maximum width of the pulse? What can be the maximum width of the pulse? Maximum width of the pulse is equal to only up to the pi, na? Whether my this positive pulse can extend after pi, beyond pi? No. So maximum value of the pulse width is equal to pi only. And you can check whatever the pulse width we got here. Yes, whatever the pulse width we got here, which is a 2 pi by 3, na? Whether it is a less than pi? Yes, so this is acceptable pulse width. Similarly, for 3D is equal to 2 pi, where the second option is 2 pi, na? So 3D is equal to 2 pi. If you check 3D equal to 2 pi, what is the D? D is equal to 2 pi by 3. If D is 2 pi by 3, what is the 2D? Pulse width. Pulse width 2D is equal to 4 pi by 3. Now tell me, 2D is pulse width which is equal to 4 pi by 3. 4 pi by 3 means it is a 4 into 60 means 240 degree. Whether this angle is greater than pi or less than pi, this is greater than pi, and we know the pulse width cannot be greater than pi, na? So therefore this is not acceptable pulse width. Similarly, you can check for 3D equal to 3 pi, 4 pi and so on. You will be getting the pulse width greater than pi only. Okay. So if we want to remove the third harmonic from the output voltage of inverter, the required pulse width is 2 pi by 3. That is a 120 degree. Very, very important conclusion. Yes. Yes. For elimination of third harmonic, from output voltage, third harmonic from output voltage, the required pulse width is equal to 2D is equal to 2 pi by 3 radians. 2 pi by 3 radians. Alright. One more thing. If your pulse width is 2 pi by 3, then not only your third harmonic, but all triple N harmonics will be absent. I am saying all triple N, because you can check, yes, if pulse width is 2 pi by 3, here put 2D is 2 pi by 3, na? So that is nothing but your D is pi by 3. If D is pi by 3, you can check for N is equal to 9. Sine of 9 into pi by 3. What is sine of 9 into pi by 3? It is a sine 3 pi. Sine 3 pi is 0, na? So ninth harmonic is also absent. Similarly, you can check for N is equal to 15. Sine of 15 into pi by 3. Sine of 15 into pi by 3 means sine 5 pi. So sine 5 pi is 0. So again 15th harmonic is also absent. We know all E1 are already absent, and if my pulse width is 120 degree, then D is equal to 60 degree, that is a pi by 3. Then not only third harmonic, but all triple N harmonics are also getting absent, eliminated from the output voltage. Let me write. Important point. If pulse width 2D is equal to 2 pi by 3 radian, then output voltage of inverter will be free from all triple N harmonics. Triple N means N is equal to 3, 6, 9, 12, 15, 18, 21 and so on. Okay, all triple N will be absent. Very, very important conclusion. Okay, so this is what we discussed for elimination of the third harmonic. Let us have some discussion on if we want to remove the fifth harmonic from the output voltage, what is the required pulse width? Yes, for elimination of fifth harmonic, Yes, for elimination of fifth harmonic from output voltage, right? So fifth harmonic elimination means V05 should be 0 na? V05 should be equal to 0. If V05 is 0 means, yes, we will be having the fifth harmonic 4 Vs by 5 pi sine of 5d sine of 5 pi by 2 into sine of 5 omega t. That should be equal to 0 na? This is V05. So let me write 4 Vs upon 5 pi into sine of 5 pi by 2 into sine of 5d into sine of 5 omega t is equal to 0. So if right hand side is required to be 0, then sine of 5d should be equal to 0. So therefore what is 5d? 5d is equal to sine inverse of 0, which is equal to pi, 2 pi, 3 pi, 4 pi, 5 pi and so on. So this is the 5d. Sorry, 0 is also present. Sine inverse of 0 is 0 na? So that also we need to write 0, pi, 2 pi and so on. Let us check one by one out of this which are the valid pulse widths. For 5d is equal to 0. If 5d is 0 means d is 0 na? So 2d is 0. 2d 0 means pulse width is 0. This is not acceptable. Yes, no? Next, 5d is equal to pi. 5d pi means d is pi by 5. What is 2d? 2d is equal to 2 pi by 5. 2 pi by 5 means 72 degree. Is it less than 180 degree? Yes. So this is the acceptable pulse width. Similarly, 5d is equal to 2 pi. What is a d? D is 2 pi by 5 na? What is 2d? 2d is 4 pi by 5. 4 pi by 5. So pulse width is 4 pi by 5. Tell me, this is less than pi or greater than pi? This is less than pi. It is a 144 degree, which is less than 180 degree. So therefore this is also valid pulse width. Similarly, you can check 5d is equal to 3 pi. 5d is equal to 3 pi. So what is a d? 3 pi by 5. What is 2d? 6 pi by 5. 6 pi by 5 is a valid pulse width or invalid? 6 pi by 5 means greater than pi na? So it is invalid pulse width. Similarly, you can check for other values. You will be getting the invalid pulse widths. So always keep in mind, for elimination of the fifth harmonic, we are having the two valid pulse widths. I can keep the pulse width either 72 degree or I can keep the pulse width is equal to 144 degree. Is this clear? Right? Next, so let me prepare a table. Our order of harmonic to be eliminated. Order of harmonic to be eliminated. And required pulse width. Right? Yes. So if I want to eliminate the third harmonic, then what is the required pulse width? We discussed now 2d is equal to 2 pi by 3 radian. If we want to remove the fifth harmonic, then what is the required pulse width? We are having the two valid pulse widths. Yes, 2 pi by 5 and 4 pi by 5 radians. Similarly, if we want to remove seventh harmonic, how many valid pulse widths will be getting? Yes, 2d is equal to 2 pi by 7, 4 pi by 7 and 6 pi by 7. So we are getting the three valid pulse widths, very, very important. Similarly, you can check for n is equal to 9 and those things, so on. Alright? Okay. So friends, very, very important concept we discussed today, that is a single pulse width modulation technique. Right? That single PWM technique is used for controlling the output voltage of inverter and also for elimination of the specific harmonic, right? We can use the single PWM. They have framed the some questions. Actually, we are running out of the time. Okay, so that's why I am winding up. So they have asked the question, in order to eliminate the third harmonic from the output voltage, the required pulse width is, and they will give the options 120, 90 degree and so on. Okay, so it is 120 degree. Nowadays the trend is, in order to eliminate the fifth harmonic from the output voltage, they will give the options like 144 degree, 180 degree, 210 degree, 90 degree. 72 degree option, suppose it is not given, then you need to understand 72 as well as 144, these two are our valid pulse widths. If you check in the books, they have given only 72 degree, but we are having one more valid pulse width now, yes or no, right? Similarly for n is equal to 7, we can check for n is equal to 9 and so on. Alright, so friends, I hope you have enjoyed the session. We'll stop here. Thank you, thanks to all of you, and all the best for your examinations.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE postal course, mains test series and interview guidance program in ESC 2020 and ESC 2021.